In section 2.4 we will discuss the free particle, and this is the Schrödinger wave equation that we are having for the time independent wave function. When a wave function is a function of x only, means a one-dimensional wave function, then we write the Schrödinger equation like this, while potential is also a function of x only. So in a free particle, free means that it is not under any force, and force is a result of some potential. So when we say that the potential on the particle is zero, or the particle is under no force, so this potential is equal to zero, and our Schrödinger wave equation will become minus h bar square over 2m d square psi over dx square is equal to e psi. Now we can write this equation as we have done this earlier as we have done it earlier in the infinite square well as well. So I can write that d square psi over dx square is equal to minus and 2m e by h bar square and psi. So we do a supposition, and the supposition is such that we write that E, this is I know that E is equal to p square over 2m, and for waves I am having this h bar k, where k is the wave number and this is 2m. So p is h bar k, it will become h bar square k square. So if I do multiply it this way, 2me over h bar square, this is equal k square, and from here I write this k equals to 2me over h bar, and this will become square root. When this one will come in square root, then only h will remain. So this k is equal to 2me over this, and I can write this equation back, that d square over dx square is equal to minus k square psi, such that k here is a wave number. It is not a constant but a wave number. So the solution of this will be psi of x is equal to a e to the power I kx plus b e to the power. Now as we remember that in infinite square well we were having the same equation, and we wrote the solution of the infinite square well not in this form, exponential form, but we wrote that one is a sine kx plus b cos kx. This we wrote the solution in case of infinite square well. Now why we write it like this and why we write like this, let me explain this thing. That in reality these two are the same, because I know this thing, that cos of theta is equal to e I theta plus e to the power minus I theta divided by 2, and sine of theta is equal to e I theta minus e power minus I theta by 2i. So from here I can write this thing back, that this is e to the power I kx. If I replace theta by kx, then I can have this thing back. So this and this solution are the same according to the Euler formula. Then why we write it like this and why not like this one. Why we write in case of free particle like this, and why in the simple in the infinite square well we were writing it like this. Now in the infinite square well, this was actually the reason that we were having some boundary conditions, and the boundary conditions were what? That the potential inside the well was 0, but the potential on the walls was infinite. Now the particle was bound inside this well, and it was having a stationary states solution. Now in the case of free particle, this EIKX is actually representing a free particle, though it is having the stationary state solution as well, but we are having no boundary conditions on this one. It's a free particle. This particle is actually extending to infinity in the plus x direction and extending to minus infinity in the minus x direction. So we have no restriction on this particle to be bound anywhere else, and this is the reason that if we write this solution in this form, then we cannot get the result easily from it. So we will have to write it in exponential form, and this way this particle will give us the moving particle, means a freely moving particle. So now is our particle is having no restriction in the space. It is free to move in the space. So what about this particle? Means when it is having no restriction in the space, then what will happen to the wave function of this particle with respect to time? Means if you leave the particle at time t0, then what will be the status of the particle after time t? So what will happen to the wave function after time t? And we know that the time dependent portion of the wave function was e to the power minus I e t over h bar. This we know from our previous knowledge. So E is h bar square k square over 2m, and this will actually make this result that when this h bar will only simplify, and we will have this thing equal to, when I write here as well, so the equation will become psi x t will be equal to AEI, and if I take k is common, let me write this one kx plus b e to the power minus I kx. This is the wave function, which wave function is only a function of x. And now I will have to write with this one e to the power minus I e t over h bar. So this portion will be actually the time evolution of the wave function. So we will have our wave function like this, and let me write this one is psi x t will be equal to AEIKX. This will actually multiplied with this, and this will be multiplied with this, and it will give us IKX minus IET over this. Let me take IK common from here. So this one is h bar, means square cancel with 1, so h bar k square, 1k is taken as common. So this equation will become a e to the power, and I take ik as common, then it will be x minus ik taken as common, x minus h bar and k by 2m and t, plus from the next one I will take minus ik is common, and it will become x minus h bar k over 2m and t, but this one will become plus. So we are having our wave function is like this, and this one I can write. We know that exponential should be dimensionless. So if this is x minus this, it means this is also x. So this is x minus h bar k t over 2m. Now this one from the dimensional analysis should be x. Now how this can be x when this is v? Then vt is equal to x. So we are having that v, the velocity, is equal to h bar k over 2m. So I can write that this is x plus minus and plus and h bar k t over 2m. This is equal to x minus plus vt, where v is the velocity of this wave. Now here, if I look to this expression, then this expression tells us that this v is equal to constant, because this one is x minus and this one is x plus. V is constant while t is changing, x is changing and t is changing. X and t are changing. X and t are changing while the speed of the wave is constant. So the wave is actually maintaining its shape. Means all parts of the wave are actually traveling at the same speed, and that same speed is actually equal to v, and we are having the expression like this one, that this is x minus and plus vt. So let me further explain this thing, that how this wave function is behaving. Let's consider a coordinate system, and along this axis we are having positive x and this negative x, and our wave is actually going, if it is going this way, then what will happen? This will actually, if it is going this way, then the x is increasing with time. Means this will be x plus vt. So as the time goes on, our velocity is constant and time is increasing, so the wave is going in this direction. As a result, x is increasing, means this is now the total distance. At each instant of time, the net x is actually increasing, and if our wave is going this way, then our x is decreasing because this is the increasing x direction. X minus vt will actually means this vt is subtracted from x. So as a result, the net x is decreasing. Here vt is added to x and it is increasing. And we say that when it is x plus vt, the wave is actually going in the right direction, the right hand side, while when it is x minus vt, it is going in the left direction. So here we are having this one, x minus this. It means that this portion of the wave is going to the left, while this portion of the wave is going to the right. So it is now, if I remove the coordinate system, then it is the same wave, just only the direction of it has been changed. So I can write that this portion, the sine xt, which is equal to aei k, and x minus h bar k over 2mt plus b e to the power minus I k, and x plus h bar k over 2m, h bar k over 2m, and t as well. So this wave is actually the portion of a wave, and this is going to the right direction, while this portion of the wave is going to the left. So it is the same wave, only its direction changes, and I can now combine these two into one. I can now combine these two into one, and it will be that sine of k. I will write this index, and sine of kxt is equal to constant a e to the power I k, and this is x minus, let me take I is common, minus h bar k square over 2mt, and this expression is that k is equal to plus minus 2me over h bar and square root. Now it is the same expression. Now when k is plus, then here we will have minus, and this will be aik. So the negative, instead of writing them in two terms, I have included the negative sign inside k. Now look here, this is k square. When k is square, so it doesn't matter we write it plus k or minus k. Here it does matter. So when we write k here plus, then it will be ikx, and when we write k minus, then it will be e power minus eikx, and this will tell us that when k is negative, means k is less than 0, then we are having the wave traveling in